Alright guys, welcome to video 5 for Unit 1. This video is going to focus on launches that are vertical, so they just go straight up and then straight down. Now, obviously we know in the real world that launches usually don't go straight down. Usually there's some horizontal component to them. Like, for example, if I'm standing on a ledge and I'm throwing a ball, it doesn't go straight up and straight down, right? Usually, I mean, you can toss it right up and then right up down. But first of all, not only are you a human, which makes it really difficult to precisely go up and down, right? But also, if you're going to throw it off that ledge, you're usually going to throw it, in front of you and, ahead of you. And so there's, vertical and horizontal component to it. However, we're going to just keep it simple today. We're going to stick to vertical launches because, it's just simpler. It helps to serve as an introduction to those angled launches. And angled launches will be something that we explore next video. But yeah, first we're going to talk about vertical launches today. Today we're going to go through two different scenarios with some little practice problems in each scenario. So let's get started. Our first scenario is we have an object being thrown upward at 50 meters per second. So I'm going to write this at the top of the screen. Forgot the is. Thrown upward 50. That's a horrible 5. That's a little better. Still not great, though. Now, yes, 50 meters per second is quite fast. I don't remember the exact conversion, but regardless, it's fast. I don't care. I'm sticking with 50 meters per second. I could change it, but I don't care. Okay. So our first problem, let's try this. What will this object's velocity be after 8 seconds? Alright, assuming that you've given this a shot. Something that I find really valuable whenever it comes to approaching any of these kinematics problems is to always write down the variables that you know. In this case, we know that our initial velocity is equal to 50 meters per second. Now that our initial height is equal to 0, because we're at the ground, right? 0 meters, don't forget the units. We know that the time elapsed is equal to 8 seconds. And we know that the acceleration is negative 9.8 meters per second squared. Why is it negative? It's because that in the problem, it states that it's thrown upward at 15 meters per second. So that implies that the upward direction is positive. While usually we do consider the positive direction to be upward, there are cases where it's downward. But in this case, the positive direction is upward, which means our acceleration, which is downward, must be negative. Anyway, now that we have all of these variables, we are at the point where we can pick a UAM equation to use. These were introduced in an earlier video. I believe it was video 1. Yeah, video 1. Yeah, so UAM 1 is V equals V naught plus AT. UAM 2 is X or Y equals X naught plus V naught T plus 1/2 AT squared. And UAM 3 is V squared equals V naught squared plus 2A times the change in position. You don't have to know those equations off the top of your head. On the actual exam, you are given an equation sheet, and these UAM equations are the first 3 equations on that sheet. I personally just find it handy to have those memorized. Again, though, you don't have to actually memorize them. Anyway, we know these 4 variables. So we have to pick an equation where all of the variables are variables that we know, but it also has to include the variable that we're trying to solve for, which in this case is the final velocity. I forgot the dot on the question mark. Now that we have this painted out, it becomes kind of clear to use UAM1. So UAM1, V equals V naught plus AT. Usually whenever you have these equations, it's a good idea to try to isolate the variable that you're trying to solve for. In this case, UAM1, it comes pre-isolated for V, so we don't have to do any work. So, yippee. Because of this, we can just start plugging in numbers. We have V must equal our initial velocity, which is 50 meters per second, times the, plus the acceleration of negative 9.8 meters per second squared, times 8 seconds. This is equal to 50 meters per second plus, time to use my calculator here, negative 9.8 times 8. That is equal to negative 78.4 meters per second. The reason why it's meters per second is because that's squared and the seconds cancel out, right? So then now we just add that to 50. So this gives our velocity is negative 28.4 meters per second. So with this, we can say that if this object is thrown upwards at 50 meters per second on Earth's surface, of course, because other planets don't have this downward acceleration of 9.8. If it's thrown upward at 50 meters per second, then after 8 seconds, it will have a velocity of 28.4 meters per second. But we want to add that key part, it's downwards. That downwards part is indicated by the negative in our answer. Let's move on to the next problem here. What is this object's maximum height? All right. Again, we want to start by writing down all of our variables. A lot of our variables are somewhat similar to the previous problem. Initial velocity is 50 meters per second. Initial position, or initial height really, is equal to 0 meters. Our acceleration is equal to negative 9.8 meters per second squared. And we're trying to find y. Now, here you might be thinking, we don't have enough variables, right? Because UAM 3 is the closest, but we're missing final velocity. Well, it turns out you actually do have the final velocity. Whenever something is at its maximum height, it has 0 velocity there. So that means we can say that when it's at maximum height, the final velocity is equal to 0 meters per second. And now we have all of the information that we need to use UAM3. We have v squared is equal to v naught squared plus 2a. In this case, is the change in y, which I'm going to write as y equals y naught. Now I begin isolating for the variable y. This gives us v squared minus v naught squared, which is equal to 2a times y minus y naught. This is equal to v squared minus v naught squared divided by 2a. That is equal to y minus y naught. Then I just add y naught to both sides to get that y, or the final maximum height in this case, is equal to that plus y naught. Now that I've isolated for y, I can just start plugging in variables. However, before I do that, there are some handy things I can do. In this case, our initial height is 0, so I can just cancel that term out. The initial velocity is 0, so I can cancel that term out too. So this is really just y is equal to negative v naught squared divided by 2a, which is equal to negative 50 meters per second squared. It's important to keep that negative on the outside, by the way, or else you end up getting a negative answer, because on the bottom is negative 9.8 meters per second squared. 50 squared is 2,500. This is negative 2,500 meters squared per second squared, divided by negative 19.6 meters per second squared. If I throw this into the calculator, 2,500 divided by 19.6, this gives a maximum height of about 127.55 meters. So that's the maximum height. We have a maximum height of 127.55 meters. Now, you know what? Why not? Since we know what the maximum height is, let's try to find what that time to reach the maximum height is. Give that a shot yourself. Alright, assuming that you've given it a shot now. In this case, there are two different equations to choose from, but again, we're going to start by writing down the variables that we know. We know that our initial height, is equal to 0 meters. Now we know our final height, or maximum height in this case, is 127.55 meters. We know that our initial velocity is 50 meters per second. We know that our final velocity is 0 meters per second. We know that our acceleration is negative 9.8 meters per second squared. And we're trying to find t. Now, like I said, in this case, there are two different equations you can choose from. You can use UAM 1 because you have v, v naught, a, and t. But you could also use UAM 2, provided that you're okay with working that quadratic equation. You know, let's do both. Why not? We should get the correct answer, so if I don't, then I know I messed something up. Hope that doesn't happen. Let's see here. So let's see. I'm going to do the UAM 1 approach first. I'm going to pick a different color. UAM 1, let's do orange for that. I'm going to slightly decrease my pen size. So let's see, I have v is equal to v naught plus at. This means that v minus v naught divided by a is equal to t. Now I can plug in numbers, that v cancels out, so that's just negative 50 meters per second divided by negative 9.8 meters per second squared. Calculator. So time is about 5.1 seconds. Gonna do UAM2 now. Let's do a little. I don't think I've used a pink in any of my videos. Let's use a pink. I've probably used pink at least once and I'm just being dumb. Y is equal to y naught plus v naught t plus 1/2 at squared. Let's see, so then, I'm going to start by canceling out this y naught term because our initial height is 0 anyway, so it makes it a little easier. Y minus v naught t is equal to 1/2 at squared. Actually, no, wait. I have to use the quadratic formula on this. This is actually kind of annoying. So if I have to, I'm going to rearrange this in standard form. Let's v naught t minus y. Standard form is just where like the variable in question, it goes from the highest degree to the lowest degree. In this case, the variable in question is t, and the highest degree term is the 1/2 at squared term. Anyway, now I'm going to start. In this case, I kind of can't really start by isolating the t variable because it happens to be in both terms. So I'm going to choose to plug in my numbers first, and then I'm going to apply the quadratic formula. So let's see, I have 1/2 times negative 9.8 meters per second squared. I might run out of space here. Plus 50 meters per second times t minus 127.55 meters. Okay, that barely fits. It fits though. I'm going to simplify this a little. Let's see. So that's just negative 4.9. Negative 4.9 t squared. I'm going to drop all my units in here just because it takes up so much space. In reality, you shouldn't drop all of your units, but it's just what I'm going to do here. Because, like I said, it's saving space. Now it's quadratic formula time. So let's see. T is equal to negative b, which in this case is negative 50, plus or minus the square root of b squared, that's 2500, minus 4 times negative 4.9 times negative 127.55 all over 2a. A is negative 4.9, so this is going to be over negative 9.8. Erase that little line there. Let's see. Negative 4 times negative 4.9 times negative 127.55 gives, oh wow, it gives, let's see, that's negative 50 plus or minus the square root of 2500 minus 2499.98. Yeah, that's basically 2500. I'm just going to completely cancel that out because, 2500 minus 2499.98, that's basically 0, and the square root of 0 is 0, so there really isn't anything. This just ends up giving this. I can add my units back now. Meters per second squared. And this is just the exact same thing as UAM1, but with a lot more steps. So probably don't want to use UAM2 here, but if you want to do the quadratic formula for fun, then go ahead. But we already know that 50 over 9.8 is about 5.1 seconds. So regardless of which equation you choose to do, you end up getting the same answer of 5.1 seconds, which is a good sign. You don't want to have done it 2 different ways and gotten a different answer the 2 times, because that indicates that you messed up at least once, right? Alright, well now that we have the time to reach the maximum height, let's find the time it takes to fall from maximum height. Alright. With these kinds of problems, with like maximum height and all that, I usually find it useful to chunk the trajectory into 2 parts. In this case, we're focusing on the part where it goes from maximum height to the initial height. Using that, we can start writing out some variables. In this case, if we're going from maximum height to initial height, that means our maximum height or our initial velocity is the velocity of this object at maximum height. And we know at maximum height it has 0 velocity. So that means our initial velocity is 0 meters per second. Our initial height is maximum height, so that's going to be 127.55 meters. Our final height is going to be 0 meters. Acceleration is equal to negative 9.8 meters per second squared. Time is what we're trying to find. Which equation should we use? The best equation in this case, it's probably going to be UAM2. Actually, what am I saying probably? You kind of have to use UAM2. What am I saying? Anyway, yeah, so y is equal to y naught plus v naught t plus 1/2 at squared. The good news is that this time we don't have to do any quadratic formula shenanigans because our initial velocity is 0. So that middle term actually just cancels out because 0 times t, it's still 0. So that term really doesn't do anything. Additionally, that term is pointless. Yeah, that's all the canceling can do. So now I have negative y naught is equal to 1/2 at squared. So negative 2 times negative 2 times the initial height divided by the acceleration is equal to t squared. So then t is equal to the square root of negative 2 times our initial height is 127.55 meters over acceleration is 9.8 meters per second squared. Plug this into the calculator. Give me a second. Negative, whoops. Oh god, I'm messing up. Let's see. Fraction. Negative 2 times 127.55 over 9.8. I need a negative in front of that. This gives 5.102. Now you notice that this time is extremely similar. In fact, it's basically the same as the time to reach maximum height. And this makes sense because you're going from the initial height to the maximum height and back to that initial height. It makes sense for those two parts of the fall to have this to take the same amount of time, right? At the end of the day, you're under the same acceleration, that is the acceleration due to gravity, and nothing else changes. You're just moving from one point to the other. And because that, like, going from that initial height to the maximum height is 1/2 of the fall, or rise, the launch, I guess. Maximum height to back down to the initial height is the other half. It makes sense that those two should be the same because they both make up half of the fall, launch, whatever. I think that's enough of that scenario. Let's move on to a different scenario. We'll say a person is standing on top of a building that's 100 meters tall. There they throw a ball straight up at initial velocity of 17 meters per second. This is going to take a while to write down, so bear with me. I can condense it a little though. So that's 100 meters, 100-meter tall building. There, they throw a ball upwards at velocity. Okay, there, that fits. Just for the sake of this problem, we'll assume that once the ball is thrown up, it's going to fall all the way down to 0 meters. It's not going to go from 100 meters to maximum height back to down to 100 meters. Yeah, I think that's all I was going to say. Yeah. Yeah, I can't think of anything else to that. Let's see. First little problem in this. Well, no, I guess this is a mini problem inside a broader problem. What's the time to reach maximum height? All right, let's assume that you have given that a shot. For this one, again, we're going to start by writing down our variables. Initial velocity, initial meters per second. Acceleration, negative 9.8 meters per second squared. Initial height is equal to 100 meters, our final velocity, which is the velocity at maximum height, is of course going to be 0 meters per second, and we need to find time. With this, it's pretty clear we want to use UAM1, so we're going to use UAM1 here, v equals v naught plus at, and now we isolate for t. This one's a pretty quick isolation. Now we can just start plugging in variables. That cancels out, so that's just negative 17 meters per second divided by negative 9.8 meters per second squared. Calculator, negative 17 divided by negative 9.8 is, got a question mark there, it's equal to 1.734 seconds. I should note with rounding, it doesn't really matter. I personally round, no, I don't round. I usually just cut off the decimal. I think it's called truncating. I don't know if I'm pronouncing that correctly, but you could probably look it up. I don't remember what it's spelled. But I, like, if it's, like, for example, my calculator right now, it says 1.734693878. If you were rounding that, you would probably round it to 1.735. I just truncated it. I just cut it off. It doesn't matter really, because on the AP exam, there is a little bit of like wiggle room with these rounding things. Also, some people use 10 for the acceleration because 9.8, 10, they're really similar. So there's some wiggle room on the AP exam. However, don't depend on this wiggle room. You still want to get it like very accurate. You want the margin of error to be really small. I personally usually like to go out to either the 1000th digit or the 100th digit, but no, not digit, place. Yeah, 1000th place or 100th place. But really, you do you. Anyway, next little sub problem. What is this ball's maximum height? Oh no. You know what? It's fine. I'm gonna cover up the problem. Hopefully you guys remember that. Alright, yeah, ball's maximum height. Alright, let's assume you've given this a shot. Again, we want to start by, yes, you guessed it, writing down variables. So initial velocity is 17 meters per second. Acceleration is negative 9.8 meters per second squared. Initial height is equal to 100 meters. Final velocity, which is the velocity at maximum height, is 0 meters per second. The time to reach that maximum height was 1.734. And we're trying to find, whoops, that's a really bad Y. Alright, so based on these variables, you can really use either UAM2 or UAM3. It just depends on your personal preference. I'm going to show both because, honestly, why the heck not? UAM2 says VY, whoops, nope, that's wrong. Y equals Y naught plus V naught T plus 1/2 AT squared. So then y is equal to 100 meters plus initial velocity of 17 meters per second times 1.734 seconds plus 1/2 times negative 9.8 meters per second squared times, put this in parentheses, 1.734 seconds squared. Anyway, I'm just going to throw this all into my calculator all at once. 100 times 100 plus 17 times 1.374. Nope, I didn't put that wrong. 1.734, not 374, plus 0.5 times negative 9.8 times 1.734 squared. This gives a maximum height of 114.74 meters. Now let's use UAM3 here. Again, it really doesn't matter. I'm gonna do a, what color should I do? How about this little maroon red? That looks black. Oh, forget it. V squared equals V naught squared plus 2ay minus y naught. Again, I'm doing this to make it a little easier to isolate for y. Let's see, that cancels out. So now we have negative V naught squared divided by 2a plus y naught is equal to y. We saw this derivation before. Don't remember where. I think it was here. Yeah, there it is. Well, actually, no, it's really down there. But it should include that. But I canceled that out because in this problem, initial height was 0. Anyway, that again, these types of things you don't have to memorize. It's just that I've done these for a while, so I kind of know these derivations quickly. You aren't necessarily expected to quickly know these derivations. You should just know how to get these derivations. Anyway, plugging in numbers, negative 17 meters per second, parentheses, squared, divided by 2 times negative 9.8 meters per second squared. And then I add 100 meters. Y equals, of course, negative 17 squared divided by negative 19.6 plus 100. This gives y is equal to 114.74 meters, which is the same thing. That's what we want. So, yippee for us. Next little sub problem. What is the ball's total time in air? Notice I'm asking for total, not time to reach max height, not time to fall from max height. The total time in air. All right, let's assume you've given this a shot. I think one of the best ways to approach this problem is to chunk it up. Instead of trying to deal with the entire fall at once, you should chunk it up into the total, I'm going to write this out. The total time in air is equal to the time to reach max height. Oh my god, I cannot write English. Time to reach max height added to the time to fall. Now, fortunately, we already solved for the time to reach max height. We did that here. That was 1.734. So now we have the total is equal to 1.734 seconds plus, and now we have a little kinematics thing. We want to find the time to fall from max height. Well, at maximum height, the velocity is equal to 0. We calculated for the max height earlier, 114.74. 114.74. Final is 0. We don't know final velocity. We don't know time. That's what we're trying to find. Got my units. And yeah, t is what we're trying. Whoops. Why am I writing 3? I want to write a question mark. I think the best might be UAM2. I think UAM2 works. Yeah. Y is equal to y naught plus v naught t plus 1/2 at squared. That cancels out because our velocity is 0. That cancels out too. So negative y naught is equal to 1/2 at squared. So then negative 2 times the initial velocity divided by the acceleration is equal to t squared. This gives t is equal to the square root of all of this. So 2 times 114.74 meters divided by negative 9.8 meters per second squared. Oh, calculator. See, negative 2 times 114.74 divided by negative 9.8. So the time to fall from maximum height is 4.83 seconds. Now I just have to add these together. So I have total equals 1.734 seconds plus 4.83 seconds. If I add these together, 1.734 plus 4.83, this gives a total time of 6.564 seconds. That's the total time in air. Again, it's important to be able to chunk this fall into parts. It makes it so much easier to handle. It's just good, technique, I guess. There's probably a better word for technique, but that's the word I'm going to choose. One more here. Let's try to find the impact velocity of this ball. Impact velocity is the speed at which an object falls into the ground, basically. So again, we want to start by just writing out our variables. We have the initial velocity. Actually, no. I'm going to go back on that. With impact velocity, it's really useful to focus on the part where it's falling from maximum height, because that way the final velocity is when it reaches the ground, or y equals 0 meters. And using the reference point of maximum height makes it easier to handle. We have, and so if it's at maximum height being our initial point, that means our initial velocity is 0 meters per second. Our acceleration is yet again negative 9.8 meters per second squared. The time to fall from maximum height is what we found just a little bit ago, 4.83. So we can bring that over here, 4.83 seconds. We know our initial height, which is the maximum height, is 114. I don't remember what it was. 74. 114.74 meters. Final height is equal to 0 meters. With this, I'm pretty sure you could pick a couple of equations. I think you could do UAM 3 if you wanted, but UAM 1's the simplest. You know what? I'll just do both. Why the heck not? So UAM 1, we have V is equal to V naught plus AT. That's already isolated for V, so we have, there's no V naught term, so V is equal to negative 9.8 meters per second squared times 4.83 seconds. Calculator, negative 9.8 times 4.83. This gives out an impact velocity of 47.334 meters per second. If we try UAM 3 here, we have V squared is equal to V naught squared plus 2a times the change in height. There's no V naught term, so this is just V is equal to the square root of 2a times the change in y. I'm going to quickly rewrite change in y as y minus y naught, because why not? Haha, funny. 2 times negative 9.8 meters per second squared. There's no y naught term, so that's just multiplied by the height. Calculator, square root of... Oh, this actually gives an issue. Oh, I see where the issue comes from. It's not the y naught term that cancels out. It's actually the final y initial that cancels out. So this is actually y minus y naught. The y cancels out because it's the initial height that no, the final height that's 0. So that means this is actually a negative. Yeah. Now I just plug this into the calculator. So square root of 2 times negative 9.8 times negative 114.74. This gives a velocity of 47.42 meters per second. You notice that these technically are different values, but frankly, they are close enough. It's honestly probably just a small rounding issue that I made with, like, whether it's this time or this height. It's rounding, it'll be in the margin of error. And also, because it's going downwards, we just want to add that it's going negative. Usually the equation does tell you that. UAM 3 with the square root doesn't always tell you that, but, if you know it's going down, then make sure to add that negative. Wow, this was a long video, 33 minutes as of this point. But that wraps it up for this video. This was about vertical launches, and like I said, I started a video, which was half an hour ago at this point. Next video 6, which is the last video for Unit 1, we are going to hit angled launches. It'll be similar to this video. We have like a broad problem and some sub-problems, but that will be something for next video. I'll see you there. Goodbye.